Dois,
Hello, everybody. Welcome to the second physics fight of the Brazilian Physicists Tournament. This is room B, and we're going to have two teams competing. The team from the Federal University of ABC and the team from the University of São Paulo. This is room A. Sorry. Yeah, it's room A, not room B. And yeah, we're gonna have a nice discussion between these two teams. First, I'd like just for every jury member to present themselves. We can start maybe by Pierre Louis, if you can just say who you are, where you're from, and what you do, more or less. Yeah.
So hi, I am a professor at the Federal Unicamp, but I came originally from the Federal University of Minas Gerais. That's why. I work at Unicamp. I work with quantum optics there.
Cool. Okay, thank you. There's also Professor Birajara.
Hello, everybody. I am Bira, Birajara Gero. I am from UFMG, and I work with biological physics. I hope we have a nice fight this afternoon.
Cool. We also have Professor Claudio Lenz.
Hello, everybody. I work at the Federal University of Rio de Janeiro. I work with antimatter and matter doing laser spectroscopy of hydrogen, anti-hydrogen atoms, molecules, and ions. And I enjoy very much these real world problems here in this tournament.
Yay. Okay, thank you. We also have Ian Braga.
Hello, everybody. I'm Ian. I'm doing doctoral at UFMG, and I work with stochastic process and evolution. And I wish you all a good fight today.
Thank you. We also have Professor Leandro Tesler.
Hello, I'm Leandro Tesler. I'm a physicist at Unicamp, like Pierre-Louis. I'm an experimental physicist, but lately I've been very interested in machine learning and artificial intelligence, and I hope we have a very nice fight.
Thank you. We also have Diogo Almeida.
Hi guys, I am Diogo. I'm also from Unicamp. I'm a postdoc, and I mostly work with ultrafast spectroscopy, coherent or not, of nanomaterials. And I'm very much experimental. I hope we have some good fights.
Yeah, me too. For the experimental team, yeah. And also we have here the presence of a really cool person that decided to join this year in our jury team. It's Professor Débora Menezes. Please introduce yourself. We're really happy to have you here. Yay!
Hello, everybody. I'm Débora from the Federal University of Santa Catarina. And at the moment, I'm the president of the Brazilian Physical Society. And I'm a nuclear physicist and very theoretical. And I work mainly with application to nuclear astrophysics as the interior of compact stars, neutron stars, white dwarfs. And I wish we all a very interesting afternoon. Have a nice fight, you all.
Yay, thank you so much. Yeah, indeed, let's see. I think we're going to have a nice afternoon. Usually we do have lots of fun here in the BPT, but, I'd like to welcome you again. Thank you so much for joining. And also now I'd like to ask the teams to present themselves. First, the team from Unicamp. Sorry, Unicamp is not even here. I'm sorry. I read the name, but I said the other name. No, the team from the Federal University of ABC. Please, if you'd like to introduce all the team members, just show up and say hi.
Hi everyone, I'm Rodrigo. Yeah.
Hello everyone.
You can also say like, I'm on the second year or something like that. Like, yeah, you could.
Oh yeah, so I'm doing overtime already. I'm finishing my master's, so I'm the only one here that has already participated in a BPT.
I'm a debutant here. is my first time, my first flight.
Hello, everyone. I apologize at first for not having a camera, but my name is Thiago, and I don't know in what year I am in UFABC because it's a very complicated thing, but one day I'll finish.
Hello guys, my name is Leonardo. I apologize. I also apologize for not having a camera, but I'm a third-year student on UFABC, and that's it. I hope we have a great flight today.
There's also Vinicius Passos. Yeah, you want to introduce? Yeah.
Hello, are you listening to me?
Yes, we can hear you.
I'm Vinicius Passos. I'm from FABC. Oh, sorry. I'm in the third year, and this is my first time participating in the BPT.
Cool. Thank you so much. Now I'd like to ask the team from the University of São Paulo to present themselves.
Hello, I'm Lauro. I just entered the graduate program of University of São Paulo in the Institute of Physics. I'm doing theoretical condensed matter. And I'm the team leader of, I'm the team captain of USP team.
Yeah, hello everyone, my name is Bruno. I'm going to my third year of the physics bachelor at the University of São Paulo. And I really like theoretical physics.
Yeah. Cool.
Hello everyone, good afternoon. I'm Mateus. I'm also in my third year of the Bachelor's for Physics in the University of São Paulo. I'm very much experimental physicist. And it's my first time on BPT too.
Nice. Okay. Well, Mariana this year is not participating on the USP team, right? But you know, she's also here as a spectator. Then, okay. Now let us start then. So we're gonna start with the physics fights. But first we have the captain's fight. So the captain's fight will decide which team will decide first or second. So let's see. Okay, so I'm gonna let me just tell you the rules once again. So the teams will have 3 minutes to solve the problem that we're gonna share here. And after those 3 minutes, I'd like you to well, maybe we can do the same thing as we did on the first fight, and you can just point your solutions, like the final answer, on the screen, and then we'll take notes. Because I feel that worked the first time. So just reminding ourselves that ideally the students should also do this alone, because in the international stage, people are not allowed to have help from anyone. So both captains will be challenged, and they can do this thing on their own only. So okay, I think you can all see my screen. So I'm gonna read the problem, and then I'm gonna give you 3 minutes after I read what the problem says. So in this fight we have UFABC against USP, and let's see. So the problem for the captain's fight, I mean, are you ready? Do you have everything you got there for the physics fight? I hope so, right? Okay. So I'm gonna read the problem. The problem is coffee neutron star. Neutron stars are one of the most fascinating astrophysical objects in laboratories to study extreme phenomena. Their central densities can reach up to 10 times nuclear saturation density rho zero. At the same time, Colombia, which is the place we're gonna host the IPT this year, is the third largest coffee producer in the world. Now imagine the neutron star densities can be reached with the amount of coffee that Colombia produces. Assuming a density of 3 rho zero for the neutron star density, how greater is the volume in centimeters cubed into which we should squeeze the production of Colombia coffee in order to reach such a high density with respect to the volume of 1 1 gram of fresh coffee beans. You have 3 minutes and starting right now. Final minute. Last 15 seconds. Five seconds. And okay. So I would like both team captains to show their answers, Lauro and Lucas. So from Lauro we have, let me see. Wait, let me hold there. Let's see. 1.2236 times 10 to the minus 6 ZUSP, and then UFABC 10 to the minus 10. Okay. Right. So let's see who got closer to the answer. Captain's fight. Let's see. All right. So the final answer would be something like rho 0 equals 2.7. It starts, right, with the rho 0 equals 2.7 times 10 to the 14th grams per centimeter cubed. The coffee produced in 2020 is approximately 840 million kilograms, which gives us something like 8.4 times 10 to the 11 grams. So 3 times rho 0, as we asked to calculate it, would be something like 1.04 times 10 to the minus 3 centimeters cubed. And the volume of 1 grain of fresh coffee beans would be something like 1.7825 centimeters cubed. So the ratio of the volumes of the coffee produced and everything over the amount of 1 gram would give us something like 5.83 times 10 to the minus 4. All right. So the answers we have are 1.2 times 10 to the minus 6 and 10 to the minus 10. So let me just confirm here. I think that the USP team, even in logarithmic scale, was closer to the correct answer. Yeah, I believe that's the case. Yeah, I think it's pretty clear then. So the team from USP can choose whether they would like to start presenting, or if they would like to start opposing the team from UFABC. So what would you like to do, Lauro?
We want to start presenting.
Okay, you want to start presenting. Therefore, the team from the Federal University of ABC will have to challenge Team USP in some of their problems. Let's see. Let me just check here. What was the problem that you already opposed and presented, UFABC, just for me to know?
We opposed the sparkles problem, and we presented the chaotic magnetic pendulum problem.
So you presented the chaotic magnetic pendulum, and you already opposed which one? Sorry, again.
The sparkles. I don't.
Oh, sparkler. Oh.
Exactly. Yeah.
Okay. So for the rules, I believe then you cannot oppose any of those again. If I'm not mistaken, I think that's it. And also, Team USP already presented a problem, the fingertips, the sandy fingertips problem. Okay.
Okay.
All right. So you may start the challenges, reminding yourselves that teams now have three. The teams now have three rejections that they can make without losing any points. Oh yes, there's also a permanent rejection by Team USP. Yes, about that. It's the electrostatic lightning. Let me write this down on the chat as well so everybody can see. You cannot challenge chaotic magnetic pendulum, sparkler, sandy fingertips, or electrostatic lighter. All right? I think, yeah. I think we're good to go. Let me just see here. Electrostatic. Okay. Okay. It's another one. Okay. I was just checking if I had mistaken the problems, but no, everything is fine. So I believe we can start with the challenges then. So please, the team from UFABC, you can challenge USP in any of the problems except those that we talked about before. So go ahead, please.
We want to challenge Team University of São Paulo with air bounce.
That's a tactical rejection.
Wait, which one was that? Sorry, just for me to, I didn't hear the name.
Air bounce.
Air bounce, okay. Cool.
So then we would like to challenge Team University of São Paulo with smashing spheres.
That's a tactical rejection.
Okay. What do we do now that the timer is over?
No, just keep going. Sorry, this is just like an estimate, so you can
Okay.
keep challenging. It's no worries.
Okay, we would like to challenge Team University of São Paulo with physics math.
Oh, okay. I think the Laura's connection was interrupted. So anyone else in the team from University of São Paulo, can you tell if you can present or not the physics of math problem?
It's tactical rejection.
Okay. Yeah, we can't keep going with the challenges. I just thought they were thinking. I didn't know that I hadn't seen that he had been disconnected. So
I'm sorry. I don't know if I lost something. Did they reject?
yes, it was a tactical rejection by their team,
Okay.
the physics of math problem. So
Rise
from
in the
now
bulk.
on, okay, rise in the bulk. So problem rising in the bulk, University of São Paulo, can you present or is it a tactical rejection?
It's a tactical rejection.
Tactical rejection, okay. And then unfortunately, from this point on, you start losing some factors of multiplication on the presenting weight. So
so we want to challenge then on problem flat Earth.
That's also a tactical rejection.
Okay. Then field ball.
Tactical rejection.
which one? Which problem was that? Sorry, I didn't understand.
Field ball.
Field ball. Oh, okay.
Okay, so now I believe that we enter in the realm of problems that we have previously not been able to challenge. I think the next one would be the chaotic magnetic pendulum.
Tactical rejection. Sorry, Mateus. But sorry to intervene, but I think we should check what happens when they because they challenged all possible problems they could challenge.
Yeah, I think now the problems then they can come back, right? So yeah, let's see. You also challenged. Yeah, you can start challenging the problems, but then they challenged again the chaotic magnetic pendulum.
Yes, there was a tactical reject as well. I think.
Yeah, that was also a tactical rejection. So
okay.
So far we had 1, 2, 3, 4, 5, 6, 7 tactical rejections. And now you can challenge one more.
Okay. I think the next up is Sparkle.
Accept the challenge.
Okay.
Wait, actually, on the rules there, I was just checking again because we always do that. So instead of the chaotic magnetic pendulum, that cannot be challenged. But what can start being challenged is first the one that was permanently rejected by USP, which is the electrostatic lighter. So USP, can you present electrostatic lighter?
Is it?
Or no?
Sorry, Matheus, but from the rules it says that the items start to to be removed from D to C to B to A.
Oh, from D to C. Oh, okay. I'm so happy. Yeah. Okay. Yeah, I just read that again. Okay. Sorry, it was a little mistake. So the one that was presented by the opponents. So opponents, which one did you present on the last thing? It was
chaotic magnetic pendulum, and we oppose the Sparker.
Okay. And then you oppose the oh, so you already did by the rules.
Yes.
Thank you. Okay, Jesus Christ. And I was here worried. Okay. So I'm happy now. So the team from University of São Paulo can start presenting. I can start preparing the presentation in 5 minutes. So please go ahead. Yeah, I was just checking by the rules. I had to do it just in case we had any other further problems. So I'm sorry for this 2 minutes that we had to check. But thank you so much, Federal University of ABC, for having read the rules and knowing them pretty well. That was really interesting. So thank you so much.
So I'm going to report Sparkler.
Yes, yeah.
Can you give me co-host?
Oh yeah, let me give you, who's gonna present? Is it you, Bruno?
Yeah, it's me.
Okay. So, well, I cannot allow you to be co-host. Henrique has to do it, so Henrique,
Okay.
please allow him to be.
Yeah. Yes, thank you. Can you see?
Yes.
Yes, we're able to see it.
Recording in progress.
Okay, I am ready.
Okay, then. So, well, let me just read the problem for you all.
Okay, sorry.
So,
just stop sharing.
Oh, okay. Yeah, okay. It's just as a.
Okay.
It's a really quick one. So, sparkler burning out. Let's see, sparkler. Investigate the burning process of a sparkler. How far can the sparks fly, and what determines the size of the flame? So, team from USP, you can pull up your presentation again.
Okay.
It's a really interesting problem. And whenever you're ready, you can start.
I'm ready.
Okay, so you have 10 minutes from now on. Please go ahead.
Good afternoon, everybody. My name is Bruno from the USP team, and today I'm going to report problem number 5, sparkler. The statement of the problem is the following. Investigate the burning process of a sparkler. How far can the sparks fly, and what determines the size of the flame? So the structure of the presentation is we'll start with a brief qualitative explanation, then we will come up with a theory for the burning process. After that, we will verify this theory, and we'll do the same. We'll come up with a theory for the spark dynamics.
I'm sorry. Yeah. Hi. I think you're not on presenting mode yet. You can try again. Just try to, just so we can see on the entire screen. Everything is good.
If you have 2 screens, 2 monitors, maybe that could be a problem.
Yeah.
We're just seeing the. Okay.
Yeah, but just try to put on the presentation mode again. I mean, there's enough time for us to go through these things, so you can just try to put on presentation mode correctly, and then we can restart the time and everything. It's no problem.
No, it's I'm already in that presentation mode. I mean, for me.
Yeah, exactly. So, but we're not seeing it. I think.
Okay, I can stop sharing.
Can you just try to change slides to see if we can?
Yeah, see, so it didn't change. So maybe you can just go out of the presentation mode and come back, like the sharing your screen.
Okay.
Maybe share your entire screen or just share a PowerPoint. Try to do that. Maybe it will help. I don't know. For 3 minutes, yeah.
Is it?
It seems
yeah, but now,
it works now.
Yeah, it's working. Right. It's working now. So clock, please just set 10 minutes. Team from University of São Paulo, sorry for this. We just wanted to make sure that you would make a good presentation. So please go ahead and now you can start.
Okay, I changed the slide now. Can you see?
It's working. Yeah.
All right. I'm really sorry for that.
No problem.
So after that, we will come up with a theory with a model for the spark dynamics. We'll do the simulation, and after that, we will try to infer the size of the flame. So the qualitative explanation goes as follows. The sparkler is composed of a pyrotechnic composition, which contains an oxidizer, composed mainly by nitrates and perchlorates, a metallic fuel, can be iron, magnesium, or aluminum, and a combustible binder. It's a kind of a resin to hold the mixture together in the main rod of the sparkler. And the reaction mechanism starts when the oxidizer undergoes a thermal decomposition. And when this happens, oxygen is released. So when oxygen is released, the gas concentration inside the compound increases and it becomes higher than the outside pressure, so the metal particles eject, and also this amount of oxygen causes the metallic fuel to oxidize. And since oxidation is an exothermic reaction, heat is released, and this heat goes to the oxidizer, and then the cycle of the reaction keeps going in the sparkler. So to model the burning process, we can start with a very general equation, which is the mass balance equation. And since the compound is a solid, there is no diffusion or almost no diffusion in a solid and no convection. So this term goes to 0 and simplify with this term, which is the time derivative of the concentration of the compound equals to the reaction rate. And now to evaluate the reaction rate, we can use the reaction rate equation. And when the reaction occurs, that is, the temperature in this specific region is higher than, is greater or equal to a certain temperature T start off, associated with the activation energy of the reaction. The reaction that takes place is proportional to the rate of the reaction that takes place is proportional to the concentration of the compound. And when it doesn't happen, of course, this is 0. And this rate, this proportionality is given by the Arrhenius equation. So this is actually a function of the temperature. The higher the temperature, the higher the reaction rate. And so we use Arrhenius equation, and this F here is just a number that can be fitted by experimental data. And EA is the activation energy. It's basically Boltzmann factor, and divided by the molar gas constant times the temperature. And the other main equation is the heat transfer equation, but it's a it's a general form of the heat transfer equation. So we consider heat sources which are driven by the reaction itself. Then there is energy released from the sparks, and also energy released from the conduction itself inside the sparkler. And so kappa is the thermal conductivity, and this equals to the changing to the rate of changing temperature in the certain volume. So rho is the density, and Cp is the specific heat capacity of the compound. We can approximate this conduction by the following, because the radial heat conduction is kind of negligible. When you burn the sparkler, you don't see it's almost instantaneous. So the radial heat conduction are negligible comparing to the main direction of the sparkler. So this becomes a partial derivative only in z, where it's the direction where the sparkler is aligned. And the source term is driven by the reaction, as I said, so is the reaction rate times the enthalpy of the reaction. And the energy of the spark is a kinetic term, so it's proportional to the reaction rate. So the more the reaction occurs, the more particles are ejected. And the minus sign is there because it's a product, not a reactant. So that's why there's a minus sign. So we have two partial differential equations and two functions to determine the concentration and the temperature. When we run the simulation, we find the following. We find that the boundary of the region where the reaction is occurring goes with a constant speed, which is actually what we observe. And also there is a bias in the direction where the compound is being decreased. So as we also observe, so after a certain Z, where the reaction is mostly occurring, the concentration is maximum, and behind this Z, there's almost no reactant. It tends to zero. And the temperature also follows a similar shape. And it's also interesting to notice that the spatial derivative here is very high, so which means that this is the region where the reaction is occurring. And this is the region also where the metal particles are ejected, because it is proportional to the concentration of the gases. Well, to evaluate the velocity of the ejected particles, we can use a high-speed camera and track back the metal particles. So that's how we're done. And it's interesting to investigate the dependence on the ambient temperature of the burning of the sparkler. So we start with burning the sparkler in a room temperature at 20 degrees. So we just plotted here the position of the burst, which is this glowing part, with time. And we did the same in an ambient temperature of 160 degrees. So in the oven, we also increased to 230 and 280 degrees. And collecting the results, we found that the burning speed was increasing with the temperature. And this was kind of expected, because as you increase the temperature in the outside of the sparkler, then the temperature gradient between the inside of the sparkler and the outside of the sparkler becomes lower. So the heat flux is lower, which means that there is more energy available to keep the reaction going. So it goes faster because there's less loss of energy to the environment. Okay, so the spark dynamics is modeled by these two equations. And so the time derivative of the temperature of the sparkler is is dependent on three effects. The first one is the power radiation. So it's actually you can model the sparks as a gray body. So there's a dependence with the emissivity and the difference of the fourth power of the temperature. And also there is convection in the surface of the sparkler. Besides that, the metal particle that it's ejected is not a complete oxide. So there's an inner part of the spark, which is a pure metal. So which means that there is oxidation, and so we need to take into account the enthalpy generated by this oxidation to the overall temperature of the spark. So this is a differential equation which joins everything together. And the second equation is just the equation of motion of the sparkler. So it's interesting to notice that this mass P here indeed changes, because as the reaction, as the oxidation occurs, you acquire oxygen, so the mass changes, and you need to consider the drag force and so on. Okay, when you solve these two equations, you can try to simulate with different initial diameters of the sparkler, and you find that the lower the diameter of the sparkler, the farther it goes. Of course, considering all the effects are happening, and you can just divide the oxidation, which is the most important, and see the difference. So yeah, this is summarized in this table. And in conclusion, we can, before the conclusion, the size of the flame is actually determined by the distance where the temperature is such that the metal spark is burning in a certain temperature that is still in the visible spectrum. So it's a gray body. So after a certain temperature, it will be mostly infrared, and you won't be able to see the sparkler anymore. And also other effect that limits the observation of the sparks is the accuracy of the observation mechanism. So you need to take into account if you're photographing the sparks with which kind of lens. So these are the two main limitations to see the spark. Okay, the main conclusion is that the mass balance.
Okay, thank you very much. Unfortunately, we're out of time. But now the opposing team has 2 minutes for technical questions.
Hi, can you please go back to slide number 12? Yeah. So this bottom equation, you didn't consider in the differential equation the time dependence of the mass.
This here.
Yeah.
Yes, I just omitted the time dependence, but it does change with time, because it would be very messy.
It's like the rocket equation, right?
Yeah. Yeah, similar. It's similar. The rate of change in mass is different, but I mean it changes the mass.
Yeah. And that dissipation force there, did you consider it for your model? Is it a constant dissipation force?
Yes, this drag force was proportional to the first power of the velocity.
Okay. Yeah.
And you're assuming the sparks are spherical as well.
All right. Yeah. Could you go to slide number 5, please? Okay. Yeah, all right. So, all right. And to the table on slide 13. That temperature over there is the spark temperature, correct?
It's this temperature here is the temperature when it hit the ground.
Okay.
Yeah.
Yes.
I wanted to ask a question on, it can be this slide. My connection fell a little during the presentation, and I don't know if I missed something. Oh no, the slide 13. Okay. And I don't know if I missed something, but how did you guys measure the temperature?
I'm sorry, but we're out of time for questions. But the opposing team has 5 minutes to make their presentations. I'm sorry, it's actually you have one more minute to prepare your presentations.
Yeah, could you enable me to share the screen, please?
Oh yes, sure. Yeah. Henrique, please allow Rodrigo to present. And try to see if you're allowed. If you can screen share.
Yeah, just a minute. I got a notification here, but we're still finishing the slides.
Okay. You have like 20 seconds or something. So.
All right, so can you guys see my screen and hear me?
Yes, just check if we can put it on presentation mode. Just to see if everything is good.
So slideshow. Can you see?
Yes, yes. So you can start. It's working.
Okay.
Okay. So yeah, go ahead. You have 5 minutes to present.
All right. So hello everyone. My name is Rodrigo. I'm going to be opposing the problem number 5 sparkler. So first of all, I'd like to thank Bruno and the team from USP for sharing their very interesting results. So the problem states, investigate the burning process of a sparkler. How far can the sparks fly? And what determines the size of the flame, right? So first of all, some positive aspects. So you gave a very interesting qualitative explanation on how a sparkler actually works, right? So congratulations on that. You showed us what they are mainly made of. So that was interesting as well. Then you went to talk about the theory on the burning of the sparkler, and it was really nice. You showed us a bunch of equations using the heat continuity equation. It was really interesting, and you could see those experimental results where the temperature of the ambient did in fact contribute to the burning rate. So congratulations on that. Lastly, you also talked about the distance that the sparks can fly on that equation you showed us. So that was also nice in the simulation. But there are a few lacking aspects. So first of all, in the simulations, you showed us some plots that did not show any units in the in the y-axis and also in the x-axis. So it was a bit tough to figure out what was happening. And the position of the flame, right, that you used to measure the burning rate, you didn't show us how you actually measured that position, how that was captured, and how did you determine the error bars of your experiments. But most importantly, the problem states that you need to determine the size of the flame, and you didn't actually answer that question, right? You showed us how quickly it is burning, how that depends on the ambient temperature, but it did not show us the size of the flame and how parameters change that. Also, there are no experimental data on the sparks, only the simulations. And you didn't talk to us about the drag coefficient that you use in the equation for the sparks, which I think it's a very important part because it's what eventually stops the sparks, right? And what is the physical meaning of the drag force proportional to the velocity you showed us? So there are a few things that I would like to talk about to you guys. First, I would like to ask maybe how could we enhance the reaction to generate even more sparks? And in conclusion, would that require a bigger flame or would that require, I don't know, a more focused flame maybe? So the other question is, why do the sparks stop? So the physical meaning of the drag, right? As I mentioned. And is there a way to adapt your theory on the burning process, which is already really interesting? Is there a way to enhance this theory to describe the size of the burning sparkler, the flame, right? Also, we would like to. You did answer the air temperature regarding the flame, but would the air temperature change the distance the sparkle can travel? And how does pressure and the air viscosity influences this result? Do we need oxygen to make this reaction happen, to make the sparkler burn, or do we need oxygen only to see the sparkles far? And that raises another question: can we do this experiment anywhere else? Maybe underwater, or maybe I don't know, in space, maybe in vacuum. And finally, you showed us the temperature of your model, but would be interesting to see from the black body radiation how that could from the measurements of the black body radiation, what is the experimental temperature of the flames? We don't know actually if your experiment is even in the right magnitude, right? Maybe there's something wrong. I feel like we need to at least have a connection between the theory and the final experimental results of the sparkler. So I would like to ask you to join here, and so we can discuss a bit of these points here.
Yes, thank you very much for asking and raising these important points. So we can start with the first topic. So how could the reaction be enhanced to generate more sparks? Well, there are many parameters that can be changed. And for example, the main one, I think, is the enthalpy of the reaction. So if you change the metal that is being oxidated, maybe you can increase a lot the enthalpy of the reaction, because mostly of the enthalpy released, it comes from the oxidation of the metals still in the sparkler. Okay. But also there's some contribution of the combustible binder, because the combustible binder also burns, not only the metal oxidates. So after the reaction, it becomes only something similar to charcoal. So if you change the combustible binder, for example, from shellac to starch, it will also increase the enthalpy.
And changing this binder, it would of course change the burning rate of the sparkler itself, but would it change the sparks as well? That come out?
I'm not sure. I think so. I mean, that the temperature, I don't think it will change because it depends mostly on the oxidation after it leaves the sparkler. But I mean, the ejection speed I think would change, because the ejection speed is something that depends of the compound that is still on the sparkler. So yes, if you change the combustible binder, I think this property of the sparks, the ejection speed would change.
Yeah.
And yeah, I thought, just to complement my last answer, other very thing to change to enhance the sparks is the activation energy. So for example, if you decrease the activation energy, the reaction will be easier to occur. So in the same
Bruno,
space of time.
Maybe we could go to another points. There are a lot of discussion topics here. So let's talk to the third point here. Can the theory be adapted to describe the size of the flame? Because that's an interesting way to enhance it, right? It's actually to answer the question proposed. Yeah.
Yeah. So one way we can do this is that I mean, there's a region. I mean, if you remember the graph of the concentration, there's a region where the derivative is very high, so it's almost vertical. So in that region is where the sparks are being ejected. If you take the temperature in that ZT, if you take that temperature and couple and insert this temperature in the model of the sparks dynamics, I mean, the model would be completely connected, I believe. So we would so the theory would completely describe the and also the flame, because the size of the flame depends most essentially on the temperature that it in which it leaves the sparkler. So that's why, I mean, you can couple these two theories this way.
Okay. Yeah. So as a suggestion to you guys, maybe for the future, to try to do this connection, right? So you can plot the radius in the y-axis that you have from that from that large derivative, and in the x-axis, I don't know, maybe the temperature measured, or maybe it's the theory of the temperature. Should be nice as well. Lastly, talk about the temperature of the flames. You mentioned that the flames are actually the sparks, right? Sorry, the temperature of the sparks. You mentioned that the sparks fly from the oxidization of the metal, right? And is there a way to increase that temperature of the oxidization and maybe fuel it further, or?
Yes, one way to increase the temperature of the oxidation is to increase the oxidation rate, because the oxidation is an exothermic reaction. So this energy released from the oxidation becomes thermal energy. So if you increase the concentration of oxygen, or anyway the gas that it's being oxidated, you would also increase the temperature.
Yeah. So
all right, all teams can join the discussion now, like all team members.
All right. So if the amount of oxygen is increased, but also the pressure of the ambient air is increased with it, do you believe that it would be of benefit, or it would stand in the way of getting a greater distance, right? Because in a larger pressure, I believe that the drag coefficient would increase as well.
Yes. Yeah. Well, there are two things. The first you mentioned, I mean, the drag coefficient would be higher. So I mean, the sparks would stop closer to the sparkler. But other thing is that if you increase the concentration in the outside of the sparkler, there won't be as much as a pressure difference, you know. So because I mean, you have a very high pressure inside the sparkler and not as high in the atmosphere. So if you increase the concentration, you also increase the pressure. So there won't be this gradient of pressure, and that's why the ejection speed will be lower. However, the oxidation rate will increase because you are increasing the concentration of gas that will take part into the oxidation that increases the temperature. So this is very interesting. So if you increase the concentration of the gas in the atmosphere, these opposite things happen in the ejection velocity and the oxidation.
Yeah, it would be really
Very
interesting to see how that would affect the overall results, right?
Mm-hmm.
Yeah,
sure.
I believe that it would require some very fine experimental work. So measuring statistically how the sparks scatter, right?
Yeah, I mean, you could try to do this in a vacuum chamber. Not actually in vacuum because there would be no burst, but I mean, slowly decreasing the pressure, and to verify that indeed this is true. Like if you decrease the pressure in the vacuum chamber, there will be higher pressure gradient, so the ejection speed will be stronger.
Yeah.
And can it be done underwater? No. And actually it just it burns only a little bit of the tip of the sparkler, and after that there's no burning at all. And I mean there is oxygen, there are oxygen molecules in water, but I mean we should better investigate how the how the energy is exchanged in the boundary of the sparkler and the water. I think it's not that trivial to model like the boundary of the sparkler and air. Like I think it's more complex, and but it would require further investigation, and yes, it would be very nice to see this as well.
Yeah, I agree with you in regard of the sparks that would come out. I don't think that underwater it would be able, but I don't see why if you have a strong enough oxidizer, you would require atmospheric oxygen to make the burning of the sparkler. I believe that the inside and the binder itself could provide the required ambient to start a combustion at least, or maybe if you start a combustion outside and move it in a place without oxygen, I believe it would still.
Yeah, I mean, what you're saying is that if you start the reaction before placing in the water.
Yeah, maybe. Yeah, I don't know. I guess it depends on how strong your oxidizer is, right? For household sparklers, I guess they don't have a very strong oxidizer, so we would need to move it. But
yeah,
I don't see why with a strong enough oxidizer you couldn't.
Yeah, there would be nice to think of in a way to optimize the burst phenomenon.
Yeah.
Like what's the composition that maximizes the size of the burst. I mean, there's one thing we should keep in mind is that the fast the ejected particle is, the farther it will go, and that's why the size of the flame will be higher. So we should take this into account to evaluate.
And regarding the size of the particle, the sparks, right? You showed us some simulation results where the distance increased with a decreasing spark size, correct?
Yes.
Are those spark sizes? I don't know. Are they in the same value as the ones you encounter in actual sparkles? Like you mentioned, there was like around 1 centimeter, 2 centimeters, 7 centimeters. There was one. Is that
no, it's in millimeters?
It's in millimeters. Yeah.
Yeah, millimeters.
Okay.
And yes, the reason why the smaller sparklers travel faster is because you can think in the impulse theorem, or I mean, you have an average force which is caused by the gradient in pressure, and times the time of the ejection equals to the mass of the sparkler times its final velocity, final speed.
So thank you very much. Now the presenting team has 1 minute for their final remarks. Please go ahead.
Yeah, I would like to thank the opposing team for the very interesting questions and interesting insights. I think the discussion was very fruitful, and we could go further in the statement of we could go beyond the statement of the problem with this talk, and also the opposing team proposed many interesting ideas to kind of generalize this phenomenon and to anyway to go further in the physics of this experiment. So thank you for this, and thank you for everyone who listened to this discussion.
All right, now we have 6 minutes for the jury to make questions for both the presenting team and the opposing team. So please go ahead, jury members. Pierre-Louis would like to ask a question, so go ahead. I mean, if you want to, also the rest of you, if you want to raise your hands or anything, would be nice just to organize, but you can also just chime in the discussion and ask as well. So yeah, please go ahead.
Okay. I'd like to start asking the opposing team, why did you like the model proposed by USP?
Well, it is a difficult problem to tackle, right? So I guess they followed the literature. They actually found the only paper I actually found as well. So, and based on it, they started doing they started enhancing the theory. So that was something I couldn't myself do. So yeah.
Okay, thanks. But USP, did you test any predictions of your model?
Yes, and there are the three main ones, which is the constant speed of the propagation of the burning, and also the second is the sharp derivative, which explains the ejection of particles, and the third is the decrease in the composition of the original compound, and everything was consistent with the result of the simulation.
Okay, so it tested qualitative predictions of your model, more or less saying that, I mean, once it burns, it's gone, and then it burns slowly, right? Okay.
I mean, yeah, if you substitute values for the concentration, it would match. It did match with the simulation.
It did.
Yes, if you substitute real values for the concentration of the compound.
No, but it did match with the simulation or with the experiment? I mean, are you comparing your model to a simulation or to an experiment?
I'm talking the following. If you take a sparkler and you know the composition of this sparkler, you take notes of the density, the molar mass, and everything that is composed, and you'll see that the maximum concentration decreases as the simulation predicts. So it's an experimental result as well.
Okay, and yeah, well, I can come back later, but yeah, let's go.
Okay. Okay, thank you. So please, Professor Claudio Lenz, go ahead.
I will restrict myself to only one question. I had two, but I'll make a comment later. Did both teams, I mean, you probably both did the experiment. Did you measure the weight of the sparkler before and after, or measure the diameter? Does it fit your models?
Yes, the losing weight is actually about 0.1 grams, and this also was predicted by the simulation of the concentration.
Yeah, I did not measure several results, no.
Okay, so we move on to Professor Leandro Tesla. You can ask questions as well now.
Yeah, I have a very simple question that I saw in the simulations and the opponent didn't point out. Was you found temperatures which are much above the temperatures that you measure or that you find in the literature. How do you explain that?
Yeah, the reason is that we had to guess the temperature the temperature that above this temperature the reaction occurs. We didn't found how to calculate from first principles this temperature T star. So that's the reason why the temperature doesn't quite well fit with the observed because of this piece of
Did you
information is
measure the
lacking.
temperature? Did you measure the observed temperature?
Yes, it's below the simulation result.
But you didn't show it to us, right?
Because we didn't track.
Okay.
So it was just it wouldn't make sense to compare one measure.
What does the opponent team think of it?
Yeah, I also thought the temperatures were quite high. That's why I pointed out in my presentation the lack of experimental results regarding that matter. I think that it would require like a measurement, maybe using the black body radiation to compare the results. But yeah, I agree.
Maybe with a better prediction for the T star temperature, we would get more consistent values for the simulation of the temperature. Like you need to measure exactly the point where the reaction is beginning to occur. This is very hard to do. So that's why we had to guess, and this wasn't quite consistent in the scale of the temperature.
Okay, now Professor Birajara, you can ask a question as well.
Bruno, can you show me the last graph, like how far the particles go? And with that, I would like to ask, like, so this distance is in meters? That's it? That's right, Bruno. You are muted.
I'm sorry. Yes, it is in meters.
Okay. So what's defined the size of the flame or the sparkle in this?
It is actually the simulation was not done in the scale of the sparkler. I mean the origin of the sparks in this case was not actually from the sparkler, was from I forgot the name. It's Medio anyway, and but I mean the formation of the dynamics of the sparks are exactly the same. So that's why we chose to do this way, because that was a way to compare with something that exists.
Okay, so yeah, that I want to have some comparison with the flame, with the sparkle. How can you compare your results with the experiments that you did? You did any kind of comparison to see if that's real?
Yes, if you think of in a scale, it's kind of a consistent, because in this case the flame is about 60 centimeters, and the sparks would fly away until 10 meters. So in the sparkler, the original case, the flame is about 5 centimeters maximum, and the travel distance is 2 meters or 3 maximum. So I mean, it's proportional to the case that was found in literature. That it's a metallurgical study, so that's why we think it's
sure. But when I see this candle in a birthday party, I don't see this flying this distance, right? I don't know.
Because they stop glowing much closer, much farther from the point they rest, from the point they hit the ground. Okay. Just glow like a few centimeters, and after that they stop glowing the visible light, but they hit the ground somewhere farther.
Okay. Cool. Now, Professor Pierre-Louis can also ask a question again. Just, I think it'll be the final one, unless Professor Debra also wants to comment on something, or Diogo. But yeah, go ahead.
I just like to ask both teams, what makes the flame, what's the most important parameter for the size of the flame? The time it takes for the spark to stop glowing, or the time it takes for it to fall to the ground?
Yes, I mean, sorry, go ahead.
No, please go ahead, Bruno. I'll talk later.
Okay. Yeah, there are some ambiguity in literature about what's the definition of a spark. So if you consider the spark as the particle itself, the most important thing is the place where it hit the ground. But if you consider the spark as the particle itself glowing in the visible spectrum, then the most important parameter is the temperature, because this is what gives us the power spectrum, and I mean you can define the visible spectrum from there. So, I mean, depends on the definition that spark that you take.
Yeah, to be fair, I don't fully agree, because I guess the definition should be on what you can measure experimentally, right? So if there's something that becomes invisible and you can't see it anymore, I guess it has no value for us. So I guess the most important thing would be the distance it fades away, right? So
okay, so just I promise it's the last time. You said it's the distance it fades away. So
I believe
Rodrigo,
so, yeah.
Yeah, okay. So if that's the case, why do you think the viscosity is so important for the problem?
I think it would change the drag force, at least. Maybe there are other parameters that would change as well, but the drag should be influenced, and the velocity it escapes would change as well. So the distance would too.
All right. So okay, we're good then. Now the jury will decide our marks in 1 minute. So please, you also have the forms. If you don't have the forms, just let me know. All right. So I will tell you the grades then. I'll just get them here. So for the reporting team, we're gonna talk for their grades. Okay. So the reporting team got from Diogo a 4, from Deborah an 8, from Claudia Lenz an 8, from Leandro Tesla a 4, from Ubirajara a 6, and from Pierre Louis a 3. Now, the opposing team, the opposing team's grade, Diogo gave an 8, Deborah a 7. Oh wait, actually, sorry, I mixed here the grades. So I would just like to ask Deborah. Deborah, was the grade for the reporting team that you gave an 8 or a 7? Just to confirm.
8.
Okay.
8 for the reporting and 7 for the opposing.
Okay. Sorry then. I just got confused here on the spreadsheet. Okay. Thank you so much. So okay. For the opposing then, let me just say all the grades again. From Diogo an 8, from Deborah a 7, from Claudia Lenz a 9, from Leandro Tesla a 6, from Ibirajara a 7, and from Pierre Louis a 4. So now the jury members can also comment on their grades. if they would like to. Go ahead.
People start thinking I'm giving low grades just so I can talk more, right? But no. So the thing is, thanks for the fights. There were interesting things. I liked that FFBC took what I said about the black body radiation into their opposition. It was nice. But at the same time, you guys didn't point out the main flaw in USP's solution for me. And maybe this is because you also attacked the same group of equations from the same paper, and you were super excited that they had managed to solve it, and it was super cool. But you know, a model is different. It's not like doing exercises for a test or like studying in a book. This is a model to predict the behavior of a system, and they have a model with many moving parts, like 3 or 4 equations and many parameters that are super hard to estimate, like heat exchange parameters and whatnot. And by the way, I liked the way you replied about heat exchange underwater. I feel it's what I would say as well. So, but it's super complicated, and in the end, they've shown us simulations with predicted temperatures that are way above the melting point of iron. So it would be a super unsafe sparklet to use at home, for instance. Or so I mean, this is something that I think is very good of the IPT, and that it should be the spirit of all team, and actually the spirit of all physicists that do theory or experiment. That models typically should be confronted with experimental data, right? Otherwise, it's mostly math that you solve differential equations. Thanks.
Well, I guess as also a unicamper who gave low grades, I should comment. Well, let's start my video. So for the reporting team, I agree with Pierre. You gave a lot of attention to the models, simulations, but you lacked a connection with experiments, with data. Especially on the temperature stuff, but I think it can be achieved if you think like something like a thermite reaction, which actually can go underwater, can happen underwater. But you should show data or at least some estimates. And I think in the opponent team, they did a better job, I guess. They already actually in the first round worked this problem, and they had a little bit better of a head start, and they explored the flaws, I think, in a decent way. The flaws that the first presentation had. So that's why I gave this gap in the grades.
Yeah, Professor Claudio, if you'd like to comment, you can go ahead.
Yeah, no, I would like to congratulate both teams. I think they did a good job. I'd like to make just a few comments, few suggestions. Maybe if you first of all, you could experiment in an inert gas atmosphere using a pulse laser to start a spark. So you could leave the stuff in there and come with a pulse laser, focus it down, and I mean, most labs have a green laser, a neodymium YAG, double neodymium YAG, where you could start the sparkle from a distance and try the underwater or under some liquid or under inert gas. The other thing is, if you had access to a spectrometer or made one, simple one, and with a camera, just by looking at the colors of your sparks, maybe you can get a nice measurement of the temperature. And for looking before and after, maybe a thermal camera can give you some insight. I don't know if it will completely saturate, but maybe it can give you a nice insight on the temperature distribution. of the sparkler. So it's just these suggestions. All right, now Professor Leandro Tessa can go.
Yeah, well, I would like to comment. General comment is that I started enjoying very much this presentation, the effort to solve a complicated set of differential equations. But when it arrived to the experimental part, I was really disappointed because they didn't explore the experimental result. They had an ultra sophisticated slow-mo camera and didn't compute the distance that the particles, that sparks flew. Then they do a simulation which suppose that they flew a few meters away, and they didn't even bother to think that perhaps their model has something wrong to it. And the same goes to the temperature. I mean, physics is an experimental endeavor, and we should always take very seriously our experimental results. And we should know how to measure, and we should know what are the limitations of our measurements. And for the opposing team, okay, I really expected you to go to pick the important flaws in USP and explore, but instead perhaps you took what you knew from your experiment, the problem of viscosity and so on, and insisted in it. So that's why I gave the grade that I did.
Okay, now Professor Deborah can join as well and speak up about their grades and what their her thoughts on the first physics fights she's participating in.
I think that the way they solved the transport equations was very nice. I have some experiences with calculations of Boltzmann transport equations, and this is really complicated. And they just looked at how to approximate and to extract the things that are not important. And I was really worried about these very high temperatures, but it's also my experience that transport equations give normally much higher temperatures than what we know they are going to give. So this is something to do with how to tune the constraints and initial conditions, things like that. So there is a way of improving the prescription they've used to calculate. So I didn't like the idea, the question about viscosity, because this is really something that I really don't think it's going to influence this kind of calculations. As far as experiments are concerned, I didn't know about this, how do you say, this low motion. This is not an experiment for me, so I thought that you would really have to do some experiment and to measure that. And I think that's basically that. But at the end, when I go to a party and there will be one of those sparkling candles, I think I will stay very far away from the cake. So that's it. Thank you.
Okay, thank you so much. All right. Then I'm gonna wait. So we're gonna recess for 10 minutes. Okay, so we'll be back at 3:45, and that's it for the second round. Thank you all for the comments, and yes, thank you so much, and we'll see you again in 10 minutes. Okay, see you soon. Hello. I think. Let's see if people are back.
Hello.
Hello.
Eu tô proibida de mexer no meu vídeo.
Ih, meu Deus.
Não que eu faça questão, mas...
Como é que eu fiz isso aqui? Ah, pronto. Fiz coisa errada. Então.
Só para falar oi.
Ah, tá, não, tudo bem. O pessoal voltou aí já? Vamos ver, ó. Vamos esperar aí o time da USP já voltou.
Eu estou aqui.
Ok. Tá todo mundo aí, então. Da UFBC também? Já tá aí todo mundo?
Sim.
Iba, então tá. Então acho que pode começar, deixa eu ver. O pessoal tá todo mundo aí. Já?
Okay. So, we challenge UFMC.
Oh, okay. Yeah, we can start. Yeah, no, sorry. I was gonna start speaking English and then say hello, welcome to the second round of this physics fights. Yeah, no problem. So now Team USP will challenge Team UFABC on presenting one of their problems, but we also need to know which problems can or not be presented. That's also one thing we have to do. So I would like to know which problems did UFABC already presented? Like which other problem did you present? Chaotic. Oh yes, they talked about it. Yeah, okay. And did you permanently reject any problem or no? Okay, not yet. So we have here on our list chaotic pendulum, which UFBC has already presented. USP opposed rising in the bulk. And the other fights, USP also already presented the sparkler problem. So I think those are the ones that...
Also, there's droplets and the fingerprints they presented earlier.
Yes, thank you so much. Yeah, droplets, sandy, fingertips. Oh wait, but rising the bulk, USP presented, right? Already?
We oppose it.
Oh, you opposed. Oh, but if you oppose, you can't present, right? So.
Yeah, but
okay.
we are opposing now.
Sorry, this is a little confusing sometimes. So I think those are the problems that cannot be. So let's see. Cannot be opposed. I think those are the ones. Chaotic pendulum, rising the bulk, sparkler, and droplet sandy fingertips. So now, please, USP, you can challenge UFBC in some of those problems, the other problems.
Okay, thank you. Thank you, Matheus.
Yeah.
Well, we challenge problem smashing spheres.
Technical reject.
Okay.
We challenge problem physics of math.
Technical reject.
Next challenge is problem air bounce.
Technical reject as well.
We challenge
now
problem
on,
flat
maybe
earth.
we'll lose points. Okay, cool. Flat earth.
Sorry, which one was it?
flat Earth.
Tactical accept.
Okay, let's go.
Trying to use my own things in this fight. I see.
Yes, that's Hoots.
Yeah. So, okay. So, UFABC will present problem flat Earth. Let me just read the problem. Let me just find the problem list. So problem flat Earth asks us to propose an experiment using only a camera and or the sensors of your smartphone to prove or disprove the flat Earth hypothesis. Using the same equipment, estimate the size of the Earth with as high accuracy as possible. So that's the problem. You've been preparing yourselves for some minutes now, but okay, you have 5 minutes to prepare your presentation. Yeah.
Okay. Do I have the hold up?
Oh, you have to become co-host, right? That's what you mean?
Yes.
Okay. Please, Henrique, allow him to present. It's Thiago Oblechuk.
Yes, I can. Thank you. Can you see my screen?
All right. Yes.
Is it changing?
Yes, it changed. Yes. So,
okay.
Are you good to present then? Okay.
Yes.
So the team from the Federal University of ABC has 10 minutes to make their presentations. Good luck, and we can start the clock.
Thank you. Hello, everyone. My name is Thiago Oblechuk, and I'm going to present problem number 6, titled The Flat Earth. As Matteo said, the problem states is, propose an experiment using only a camera and or the sensors of your smartphone to prove or disprove the flat Earth hypothesis. Using the same equipment, estimate the size of the Earth as high accuracy as possible. So, there are many theories regarding flat Earth, such as the world as a disk or other geometrical shapes, such as a pentagon. But what all of them have in common is the denial that the Earth is round. And trying to explain the world around them, the so-called flat earthers try to exploit loopholes where they can use basic concepts of physics in a more complex system, such as explaining gravity as the world is accelerating upwards in the universe, whatever upwards really means, or the sunset with the concepts of field of vision or vanishing points, contrary to what Occam's razor principle suggests. Most of these claims was, however, disproved by countless of experiments performed in thousands of years, but they still claim and yell hoax to every possible given explanation, as we're somehow living in a conspiracy created by the government. I'd like to take a step back a little, and I think we're all familiar with the efforts of great scientists and philosophers who devoted part of their life to prove the world is round. And even though this group of people claim the flat Earth hypothesis was believed, accepted in ancient times, studies shows that Aristotle himself already knew the Earth was round, and Eratosthenes is credited as the first person to calculate the size of the Earth using basic concepts of trigonometry applied to shadows in the cities of Syene and Alexandria. And we cannot, however, forget we once stood on the shoulders of giants and credit every other person responsible for building our knowledge on the subject and finally removing the Earth from the center of the universe. So the question arises, is geometry the answer? Well, not by itself. The best way to disprove the flat Earth hypothesis is to prove the validity of a round Earth model by performing an experiment that would otherwise only work if the planet is not flat. Sorry. Let's state some hypotheses then. The first one is that the Earth is round. The second one is that the moon orbits the Earth. And finally, there is an apparent movement in the sky. Well, if the Earth is round, it certainly has a diameter. If the moon orbits the Earth, its orbit certainly has an eccentricity. In this case, it's very close to a circle, and that's an important fact. And also, if we take in consideration the Earth as a reference frame, we can study the movement of the moon and try to verify Earth's radius by it. And last but not least, this method is based on the article, The Simplest Method to Measure the Geocentric Lunar Distance, a Case of Citizen Science. About our methodology then, let's define phi as the angular diameter, or the ratio between the diameter of the moon and the distance from the Earth. Also, using the cosine law, we can get the following relation based on the diagram below, considering the angles HA and HT, the apparent and the true elevations of our natural satellite. I'm going to also define the relative apparent size as the alpha, or the ratio between the distance to the moon next to the horizon and at its maximum height in the sky. And if we manipulate all these equations, we get the formula for Earth's radius, as we see in here, where R of E is the Earth's radius, and D of T is the distance from the observer to the moon. About our, in this case, we will get 2 points of interest then. The first one is when the moon is closer to the horizon, and the second one is when the moon is in its maximum azimuth. And in this location, we'll take respectively 2 angles, the HT0 for the moon in the horizon and HT for the moon in its maximum altitude. And we're going to explore the changing angular diameter for the alpha, where we use in the equations. But to do so, we're going to use the pixel ratio of the photographs to get this alpha. About our equipment specifications, we use an 18 millimeters camera lens with a 15-second shutter speed on an aperture in the f11 mode with an ISO of high 2. And processing the image for a better understanding and analysis of the limits of the moon, as shown below, where the left image show a very bright spot in the night sky, with the right one being way dimmer and understandable about the limits of the satellite. That way we can start our analysis. To do so, using the Photoshop software, we stipulate a rectangle of constant height equivalent to 80 pixels and his length fitting the limits of the moon. Selecting the area of the rectangle then, we get the amount of pixels as we can see inside the red boxes in the right corner. In this case, 8829 pixels. It's possible then to fit our data in a table with the first column representing the set of pictures along with their data, time, apparent and true elevations, and the pixels analyzed. That way, it's possible to substitute the values in the previous equation for the radius of the Earth with its corresponding uncertainty. With regard to the local Earth radius, we arrive at 6,374 kilometers at the altitude the data collection took place. And to contrast both values with the mean Earth's radius, we have the value of 6,371 kilometers. Well, it's clear this phenomenon is highly dependent on weather. One of the reasons our sample space is not large during Brazil summer, but with the right climate conditions and a good camera stabilization and resolution, the uncertainty in our measurement will be significantly reduced. And with a short analysis capability, this experiment is not only easily reproducible, but extremely accessible for anyone with a camera and an image and astronomical software. Lastly, reducing our uncertainty in getting both a large sample space, the experiment seems to fit well to our model, validating the round Earth perspective. And thank you.
All right, then. Are you sure your presentation over? Okay.
Yep.
So the opposing team has 2 minutes for technical questions. Go ahead.
Hi. First of all, great presentation. Can you come back to the theoretical approach you had with the calculations for the radius?
This one or this?
This one. You say you need the distance from the observer to the moon. How do you establish these experimentally only with a camera?
Okay, this was actually taken from literature. We wanted to make sure. Okay.
Can you please go to the table you showed your main results, please?
This one?
Yes, thank you.
Okay. Another thing, you showed the error rate for the ratio and radios on uh, different dates. Why didn't you put an error to the local Earth radius and the mean Earth radius final result?
Okay, so the local Earth radius is actually it was taken in consideration a software that didn't actually give us the error it used, but it only asked the latitude. Hold up. It only asked the latitude of the place that the experiment took place, and that's the answer they gave us of 6374 kilometers.
Okay, and with the calculations that you had, you couldn't do a error propagation to determine the error of the measurements?
Yeah, the error is actually right here. We use the error propagation to estimate the error based on the pixel ratio uncertainty.
Okay.
All right, so time's up for questions. Now the opposing team has 3 minutes for preparing their presentation.
May I stop sharing?
Stop or start? Sorry. Yeah, you can start. Yeah. Hey. Who's gonna be the opposing person? It's gonna be Mateus.
Yes, it's gonna be me.
Okay, Henrique, then please allow Mateus to share the screen after. Yeah. You have 1 minute. All right, the time is
So
up.
we're ready. I'm gonna share my screen.
Okay.
Like just me. Just a second.
Can you share?
Can you guys see?
Wait, let me just see. It's not showing yet. Well, nothing is showing. Reminding that you can also ask for a timeout. Like,
can I have a timeout? I'm having some technical difficulties.
Okay, yeah, no problem. Yeah, all teams have like 3 timeouts they can ask per session.
Thanks for compartilhar. So I will try again. Here. Can you guys see it?
Yeah, no, we cannot see it. Oh, wait, now maybe.
Oh,
it's still not showing so well.
Sorry, so
there's some blocks on the screen.
Yeah, you can also ask another timeout if you want.
Now we can see it.
We want another timeout.
Okay, yes.
Perfect.
Can you see now?
So you have 5 minutes to present. It's working. So please, you can start your speech. Yes. Go
okay,
ahead.
So I'm Matheus, and I'm going to be opposing the UFMC team for the problem 6 flat Earth. So first of all, the statement, as said before, propose an experiment using only camera and or other sensors of your smartphone to prove or disprove the flat Earth hypothesis. Using the same equipment, is estimate the size of the Earth with as high accuracy as possible. So you have to propose an experiment using only your camera and your sensors of the smartphone, and you have to use the same equipment to estimate the size of the Earth with as highest accuracy as possible. So some positive aspects first. Very interesting background on the sociological aspects of the flat Earth hypothesis of today's climate, and also very good and interesting historical citations of people that already have tackled this very ancient problem. Good overview of the calculations with interesting modeling, and very interesting to see such an accessible method to measure the Earth's radius. However, a few clarifications are due. First of all, your calculations assume that the Earth is round, and then you have the radius calculated, but you never actually prove it. Like experimentally, you assume it is round, and you show a result that can or can not be disproven. How you determine the accuracy from the pixels of the picture, and how can you guys have processed the picture? So is that a factor that can alter the picture, and the pixels, are they as reliable as before the processing? How to optimize the experiment was not something that you guys specified, and didn't specify the most high accuracy possibility that you could maybe to have a more specific radius of the, not a more specific, but a more accurate radius of the Earth. How you guys have said responding to this, but it's still interesting. How do they access the distance to the moon? And this is just an overview. It's not exactly. It's just an interesting point. Is this experiment does it have to be due locally, or can you move it around to reproduce it? So these are the aspects that I think we should discuss better.
Okay. First of all, thank you for the slides, and let's start by the first one. Yes, we assumed the Earth was round at first, but as we said in one of the first slides, that was the main objective of the presentation. We would analyze a model, and if the data fitted the model, then the model would probably be right. It's the same criteria of the falsifiability method we commonly use in science. So we assumed, and by the results, we would see if our assumption was right or it wasn't. About the second one, how did you determine the accuracy from the pictures? Well, it was a really hard process to do, because I didn't have like a very potent camera. I tried to make it all the way that we could use a cell phone to picture. Like, I didn't want to use a camera with a potent, a powerful lens. So I
Hello.
tried to make.
Wait, sorry to interrupt. It's because one of the jury members has lost their connection, like it's Professor Deborah, and I would just like to ask if the teams, what do they feel it's good for us to do? Do we wait a little bit until she comes back, or do we continue the discussion? Like, we can restart the time, like you restart the discussion too. It's because she lost a part of the thing. I don't know if she's going to be able to do so. We're just waiting a little bit more.
We can wait.
Are you
Yeah.
okay? Or
are you in contact with her and something like that?
let's see. Oh, is she back? Oh yeah, she's back.
Great.
Okay, cool. It came back pretty quickly. Sorry, it's just because I was worried that it would take a more extra time, and then just having a less one jury member could be a bad thing.
Sorry
in
about
the end.
that.
No
So
problem.
yeah, okay, and we had no rules defined for that. So please, I mean, if you want to like restart even the discussion, like I remember it was pretty much in the beginning. We can also restart the clock in the 5 minutes and just move on. I think that would be the best way to deal with it. So I'm sorry
so
for
from the beginning.
Yes, please. I think we'll be.
Okay, so again, thank you for the slides, and we could just start from answering every question. The first one assumes that the Earth is round, and indeed we did that, but that was the criteria we used for the experiments, as we stated in one of the first slides. So if the hypothesis was that the Earth was round, if our data corroborate, if our data pointed that the data was right or within the limits of uncertainty to our hypothesis, then the hypothesis would probably be right. That would be the criteria of falsifiability that we commonly use in science. About the second question, how did you determine the accuracy from the pictures? And again, it was a pretty difficult task. We didn't want to use powerful cameras, so we try to use specifications that a regular cell phone would have. And to do so, when we analyzed the pictures like really close, sometimes we couldn't see the pixels very right because of the brightness. So what we do was trying just to sometimes diminish the exposure around the moon, so we wouldn't I forgot the word, sorry. We wouldn't change the pixels of the moon. We would change its neighbors' pictures, and then by seeing that the limits of the moon, the boundary, is clear, we could start doing our analysis. How to optimize the accuracy? That's one of the processes we try to do. So it was really hard to take the four corners of the moon, like make a rectangle of it. So what we did was fixating the height at 80 pixels. So every every picture we analyzed had 80 pictures height, with the length of the rectangle adjustable to the size of the moon. That way we could, by taking the ratio of these two pictures, the 80, the height of 80 would cancel out, and that would give us the alpha we needed. So I think that was a good way.
Can I ask a question about the pictures? You mentioned before that it was kind of difficult to see the pixels, and also you had to. Did you have to zoom in into the picture?
Mm-hmm. We did zoom in, and that was like a manual analysis. We tried to analyze as closer as possible to see where the limits of the moon started and when it ended.
And how can you guarantee that the zoom didn't disturb the image whatsoever? So you can do this accurately.
What? Sorry.
Well, when you zoom in, sometimes a picture can be disproportional to the original picture. How can you make sure that that didn't happen in this case?
Yeah, as we try to accommodate all the pixels the picture would present us. We zoomed into the maximum and took all the pictures the moon would present. So whatever pixel was white or in shades of gray, we would take it as part of the moon.
And you obtain the pixels by eye, or do you have a software specifically to count the pixels?
We tried to use a software, but the results wasn't taking consideration on lots of the pixels of the moon. So we kind of let go of the software and try to do manually.
And can you see how that can be problematic as of the accuracy of the problem, as your eye can really be, and this is important, can really be corroborated? So maybe you saw something and another person saw other things. Do you think maybe trying to use a software, even a simple one, that can analyze images, first of all, to understand if the zoom is really not modifying the image, and especially to verify how many pixels there are, as the moon in a picture, the moon's relatively big, not in astrophysics scales, but for a human scale, the moon is actually quite big, and in a photo, a few pixels can be quite a difference, maybe. And did you take more than 2 pictures only, or did you only take from the azimuth and from the horizontal? Like
we took two sets to join the discussion as well, so now everyone can ask.
We took 3 sets of pictures. From each set we would study the 2 positions only, the one closer to the horizon and the one closer to the azimuth. And answering the question you made before, yes, we're aware of the uncertainty of our eyes, or the manual approach, and that would probably be the reason of. That's probably not. It is the reason of some of the uncertainties we have in our measurement, as a systematic error in the experiment, and that's one of the things we'll try to explore and make it better for the next steps. Even because during summer, Brazil, it's a very rainy country, so it's really difficult to take a night without clouds. Did you ask something later? Sorry, I
think one of my colleagues have a question.
What? Sorry?
I think one of my colleagues has a question, if he wants to say it.
Okay.
Bruno?
Yes, so I just would like to point out that I think I disagree with the claim that the reporter made, that if you have an assumption and your experiment is in agreement with your assumption, it means that probably your assumption is correct. Well, this is not true. It just means that your assumption is plausible, and plausibility is far from prove or disprove anything. I mean, there are many things in flat Earth theory. I'm not a flat earther, just just kidding.
That's okay.
But yeah, but I mean, there are many things in flat Earth theory that are plausible, but are not true. So these are the reasons why flat Earth. These are one of the reasons I think that why there are flat earthers and nowadays. So I mean, to use plausibility to prove or disprove anything, I think you should use many different plausibilities, like do other experiments assuming the Earth is round and measure different quantities and always conclude the same thing. But with one method to assume the Earth is round and confirm the data, I think it's far from disprove or disprove. It's just plausible. It's just the first step to prove or disprove.
Yeah, I think we can agree in parts then. I agree with you that plausibility is not the final, like, it's not a criteria that defines something in science, because that would give us the discussion about all the white swans. If all the swans we saw in our life would be right, that doesn't mean there isn't a black swan or anything. But our criteria, apart from falsifiability, was taking the results we get and try to verify with the literature. And in terms of the claims of the flat earthers, that would be a problem maybe for if we're living in conspiracy, then the results we get are probably jinxed. But I think that using trigonometry and using elements outside of Earth, not Earth itself, would give us a very close approximation.
Yeah, but if you use equipment outside of the Earth, you are not in the statement of the problem anymore, because you have to use a simple camera in your smartphone.
Can I make a comment on that discussion, please?
Sure.
Yeah, so we did in fact assume the Earth was round to start, but if that assumption was wrong, what we would get when we measure the radius would be an infinite radius. So the fact that even for we use the distance of the moon to the Earth from the internet, but even if we use like 100 kilometers as the distance, which I don't know what is the distance flat earthers actually use, but we can use those distance, and even for that, our model would result in a finite radius for the Earth, and that is not just a plausibility, right? Is a bit more it's stronger than that.
Yeah, we see that, but that's the thing. But because you are also assuming that the moon orbits the Earth in a certain way, and they could just change the way the moon orbits the Earth, and this problem could be solved that way. And they usually do that, like change the method to agree to the data. See, so that's a point. A suggestion would be measure indeed the curvature of the Earth, which is a quantity which could say that if it is indeed flat or not. If the curvature is non-zero, so it is not a flat surface. That's a suggestion.
Yeah.
All right. So thank you very much for the fruitful discussion. Now, the presenting team has 1 minute for their final remarks. Please, just go ahead and.
Okay. So first of all, thank you for the USB team for the this conversation. I think it was really clear that both of us have information to trade about this problem, and it would be really good for us to discuss it later after the BPT. And I think we achieve the goal of the question at our limits of uncertainty. And I think that's it. Thank you for you all.
All right, then. So now the jury members can ask questions for a period of 6 minutes. So starting here with Diogo Almeida, please go ahead. Ask away.
Hi, guys. So aside from the epistemologic stuff, which I'm pretty sure Leandro and Pierre are gonna tackle. So when you presented your uncertainties, you just presented the pixel ones. So why didn't you you had the camera parameters? Why didn't you put the camera resolution into that? And this you put a filter just to reduce the intensity of the moonlight.
Yeah, we tried to we thought about getting I forgot the word, a filter, but we couldn't have access to it, so we tried our best to make this possible. It was really a household experiment we tried to do.
Okay, but what about the resolution of the camera? Why did you? But you put your uncertainty just for the pixels, which is, I don't know.
Yeah, we forgot to took the resolution of the camera in context.
Okay. Okay.
Okay, now Claudio Lenz can ask away.
I have a question for both teams about the validity of this method. My question is whether the atmospheric optical diffraction, for instance, lensing in the atmosphere, could that change completely the measurements? Could that render this method invalid? So I'd like comments from both teams.
Maybe it wouldn't invalidate, but it would certainly take into consideration to raise the uncertainties of our measurement. So if we could maybe, I would say, photograph or take the image of the moon in another spectrum of light where the interaction with the medium, the atmosphere, would be lower, I think the uncertainties would be quite lower too. That would probably give the model a more precise result.
I think the atmospherical lens effect or any other effect caused by the atmosphere can actually be really important in this situation, especially when you have such a homemade, but a simple camera. So these effects can easily distort the image. Maybe if you took in different altitudes where the atmosphere is different and more scarce, for example, in the top of a mountain, maybe you could try to see how much it affects the image, and if it is how much more accurate you can make the image and the measurements you're having.
All right, then. Now I think it's time for Leandro Tesler to ask questions.
Yeah, I don't know if you know, but I'm from a sect that instead of claiming the Earth is flat, we claim the Earth is centrosymmetric, is a centrosymmetric solid. So we have a division of cubic earthers, icosahedral earthers, tetrahedral earthers, and so on and so forth. Can you prove that we are wrong with your method? And the question is for both teams.
Using our method, no, we couldn't prove that the model would be wrong. What we would prove with our method, or at least see the results of it, was that it fits with the literature and the model we proposed using basic trigonometry. So if the Earth was round and the moon orbits the Earth, then by some trigonometry relations, we could take this result and compare with the literature.
So you cannot prove that the Earth is not flat, because in the cubic model, each face is flat.
We couldn't do it.
Okay, thank Thank you. What about the opposition? What do you think of it?
I agree that you couldn't do it, and I think that's one of the reasons maybe the presenters, the UFCM, tackled the problem wrong, as trying to falsify a theory is much more not practical, but much more validated than you trying to prove one, because you can always have some parameters that you don't account for, or some knowledge that you don't have at the moment that can affect the final result. So you can have something that is, as my colleague said, plausible, but you have information later that you have to change your mathematical modeling, and then maybe it's not as plausible as you thought. So maybe tackling the problem as trying to falsify it instead of falsify the flat Earth, instead of proving the round Earth, is maybe more definitive as a result.
Can I go? I have several questions.
Yeah, sure.
I'll try to make at least one. Can you tell me why you decided to take a picture of the moon? I mean, it's quite brave actually to take the picture of the moon with a cell phone, because it's almost an internet meme that it's the worst thing you can take a picture of with your phone. But why did you choose these specific parameters? I think it was 15 seconds shutter time, high to ISO setting. Why did you do this?
Yes,
To be the reporter, of course.
I've researched some information about astrophotography, and I thought that those specifications was the best to photograph the moon. So I tried some other.
They told you that this was the best way to take a picture of the moon?
Yes, by the researchers I did.
Because
okay,
you know what? Yeah, just I mean, what happens is that you put such a huge integration time on your detector that you saturate a lot of pixels, and then your Photoshop post processing cannot work if the pixels are saturated, because they will all come down homogeneously, and this saturated disk will never shrink the real size. Okay.
Right.
But I mean, okay, question, right? I didn't see any uncertainty on your radius of the moon, on your radius of the Earth. I mean, how precise can it be? If I take a snapshot of the moon at two different positions in the sky, can I know the radius of the moon with 1 meter precision?
Actually, we approached the problem by just using the pixel, a line of pixel as the radius of the moon. So our uncertainty on the radius of the moon would be correlated to the uncertainty of our pixel.
Okay, and how did you calculate the radius of the Earth? I'm sorry, but I saw you have a model. I saw you have data, but I didn't see any fit of the data. Did you just put the data onto the equation, calculate the results, repeat it 5 or 6 times, take the average and standard deviation, or did you do a fit?
We didn't do a fit. After we stipulated the formula, right? After all the trigonometry manipulations, we would take the data. So the ratio of the pixels, the time, so the azimuth of both pictures, and substitute on the equation. And by it, we would do an uncertainty propagation to take the error on the radius of the Earth.
Okay, thanks.
We didn't do a mean value or the standard deviation.
All right, I have
okay.
more questions.
Thanks.
If not, then I'll leave the jury to decide their marks, and we'll come back soon. let's see, I'm just waiting for us to compute all the grades. Then after, I also have to make a ratification on something. But yeah, let's see. I think we have the grades. All right, so I'm going to start giving the grades for the reporting team. Okay, so the reporter, the grade from Claudio Lenz was a 6, from Diogo Almeida a 3, from Virajara a 5, from Leandro Tesler a 3, from Deborah a 6, from Pierre Louis a 3, and from Ian Braga a 7. And now for the opposing team, USP, Claudio Lenz gave an 8, Diogo Almeida an 8, Ubirajara a 6, Leandro Tesler a 7, Débora Menezes a 5, Pierre Louis an 8, and Ian Braga a 7. Now, if the juries would like to talk about their grades, you can. This is the time. Yeah. You can just start speaking up. Oh yeah, go ahead, Professor Deborah.
Well, I can talk first.
Okay.
Concerning the reporting team, they've used a model and they've given a reference, but they didn't say anything about the model at all. There were just 2 equations. So they could have explained which were the assumptions, the drawbacks, the flaws, so on and so forth. So I missed that. So it was something simple that they could actually do with a cell phone. But you see, the explanations were just missing. As for the opposing team, I think the questions were okay, but I really strongly disagree with one of the things that Matteo said, that it would be better to falsify the flat Earth hypothesis. This is completely against scientific methodology. This is not how we do things. Actually, when we do something, we have to prove that we are right. So that's why this pseudoscience, pseudo things just spread so fast, because this is what they claim. Just prove that I'm wrong. So I don't like this idea at all. I think that you never have to prove that someone else is wrong. You have to prove that you are correct. That's what scientific methodology says. That's why I gave a 5, although I like it, all the other questions and the points that the opposing team discussed. So that's it.
Now, Claudio Lenz, please, you can ask.
My advisor used to say that the best defense is when you get the committee fighting against each other. So I would like to be completely opposite to Deborah, okay? In this sense of whether you falsify or you prove it yourself right. With this method, you don't prove yourself right, okay? You just prove that it's plausible indeed. So I agree with the opponent's view. But I think the method that they chose is completely flawed, okay? This method does not do anything good for you. I would suggest you change the method. There are easier methods and that really get rid of the flat Earth idea, okay? So that's just my comment.
All right, Pierre, we can go ahead.
Thanks. I think I'll take the middle path between the two. Actually, I think what you the best approach is, because this is a bold claim, right? The Earth is flat. And actually, I think the Earth is round. Round for me is a 2D shape. Okay, so it's another problem inside. It could be round and flat. like a pizza. But so it's a bold claim, and it has many implications. And when you start, and it's again what I said, and it's something that I really invested in, which is models make predictions about reality, and you test and you check if your model predicted the outcome or not, or you adjust your model and so on. So the more predictions agree with the given core assumptions that these models share, and Deborah was perfect in saying that. I mean, assumptions is a big part of this game, in particular here. The better you are to say that one of the explanations is more likely to be true than the other. That's my opinion. But honestly, even in not going to the philosophical, the philosophy of science part of the talk, right? Even if your method were the best method, and to completely end this dispute, the way you collected and analyzed the data was really not good, because you saturated your pixels. You could have played more around with your camera, looked for a filter. And I mean, come on, filter is sunglasses could already start working, right? A lot of parameters. And this, I mean, when your pixels saturate all the optical information that you could have, or almost all, you have the information that they're saturated, right? But all the rich information, the seas of the moon, the craters, everything is gone from your image forever. I mean, how can you, if it's everything to 155 value in pixels, how can you recover that? Okay. Not even with fancy machine learning, right? Because machine learning will look at photos of the moon and say, this is likely the moon, so it should look like this, right?
Yeah,
so there was this really deep experimental issue that I didn't like. Okay, that, I mean, for me was really a big problem. Thanks.
All right. So now Leandro Tesla also has a word.
Yeah, I will just stick to the epistemological problem, and I'm lean much more to Claudio's side than to Deborah's side. I mean, when you try to prove a hypothesis, your model should be falsible. And my sect was born from the lack of falsibility of your hypothesis. I mean, my sect of the solid flat side Earth is compatible with your model. So you didn't prove that the Earth is round with your model. And I also would like to add that I liked very much the attitude, mainly from Bruno's intervention, because you saw a model that was wrong, and he was bold enough to say to his colleagues, you were wrong, your model does not apply. And it was one of the first times I see in this context a team clearly opposing the other team and with a sound argument. So I enjoyed very much this fight. But you have to be very careful when you use a model to prove a very bold idea.
Yeah, just one comment that I forgot to make, and that goes back more to the dispute, right? I think we're more or less done, right? Which is, your first slides were really nice, right? That saying that the strategy that these guys do, that they move the goalposts when you do the experiment. They say, look, what you predicted doesn't happen. They say, no, but it's because you didn't put a bismuth sphere around your detector or whatever. And then you fell into the trap. You used data from the globalist conspiracy to prove that the Earth was a sphere, right? Because they gave you the radius of the Earth, and so this is, I mean, okay. Here I was honestly more worried about the technical aspects of the experimental method. But if you were discussing with these guys, they would point as, but you took this from NASA, and they're in on it. Like, it's obviously a projector. By the way, a disclaimer to everyone on YouTube. So.
Yeah, Pierre, could be worse. The guy could take 2 pictures of the moon and get to the same size and tell you, look, it's the same size, it's not different. The Earth is flat.
Yeah.
The Earth just, I don't know how they think about it, but
yeah. That's the thing, right? Your data processing needs to be very sharp, and you have to cover your bases. But I mean, it was a very nice fight, very good discussion.
Yeah. We are
sorry.
criticizing because that we do best, but it was nice to see the pictures in trying. So yeah, we just criticize you guys, but you did a nice job. It was good to see you fighting about it.
Another comment I would like to make in the experimental part is if it's possible to get the raw image instead of JPEG, it'll be better because JPEG hates borders. So it will blur everything that is sharp. So if you can, never use JPEG for this kind of stuff. So it'll screw things like even worse. So besides not using too much exposure, never use JPEG. Please, I beg you, never.
All right, so we're finished then with the discussions. And the comments of the jury. I have to make a ratification, as I said before, because last time, I don't know if anyone noticed this, but I did not read all jury grades, and this is a problem, of course, and therefore I will correct that now. So now I'm going to review the grades for the previous fight. Okay, so for the previous round. So just
Matheus, I cannot hear you.
All right,
I can't hear you.
So on the first fight, USP was the presenting team, okay? And then I'm gonna repeat the grades. So Diogo Almeida gave a 4, Débora an 8, Cláudio an 8, Leandro Tesla a 4, Ubirajara a 6, Pierre-Louis a 3, and I was missing one of the grades because the print I had from the spreadsheet was cutting out this part. So Ian Braga's grade was a 7, okay? And now for the opposing team, which was UFABC at that point, we had from Diogo Almeida an 8, Débora again a 7, Cláudio a 9, Leandro Tesla a 6, Ubirajara a 7, Pierre-Louis a 4, and Ian Braga, which was also lacking from last time's competition, it was also a 7. Okay, so I would like just to ratify that, and then I would also like to ask you, all. I mean, not ask you, but thank you all. If you watched through YouTube as well, this live broadcast, we'd like to thank you all for participating. And well, I think Professor Deborah wants to say something. So, I mean, she's the president. She can do whatever she wants. So go ahead.
No, just a question. Tomorrow, it is at 5:30?
Maybe for you, right? Because you're coming just for the second part.
Wait, 5:30. Wait.
For the final, for the prizes.
Okay. So the final will be from 2 to 6, I think. Right? Henrique? Something like that. Yeah.
Yeah, but I cannot make it before 4 o'clock. So somebody,
okay.
I think, somebody told me just to come for the final for the.
Okay.
I don't know if you give prizes or how it works. So this is what I want to know what I'm going to be.
So Henrique, unmute yourself and speak. I think is it? Está mutado. You're muted.
A frase mais ouvida na pandemia é "você está mutado".
Obrigado, gente. Obrigado.
Valeu, gente.
Obrigado, pessoal.
Obrigado, equipes.
Obrigado a todos.
Muito legal.